All right, so lesson 3 is solving systems of equations. And our learning target is that I can define a system of equations, and I can also find the solutions to systems of equations by graphing and or solving. So first of all, we need to define what is a system of equations. A system of equations is two or more equations that share the same variables. So here are a couple of examples. The first one is just two linear equations, right? Y equals 7x minus 3 and y equals negative 2x plus 1. Notice that those are both in slope-intercept form, right? They look like y equals mx plus b. And we're going to be focusing mostly on these types of equations today. But another example are these ones down here. These are actually also linear equations, but they're in a form called standard form that we haven't focused on quite as much this year. And so we're not going to get into quite as much of solving these today, but these are also considered systems of equations and we can solve them in similar ways. We're just not going to focus quite as much on them today. So when I say we need to solve a system of equations, what does that mean? Like, what's our goal to solve a system of equations? Our goal is that we need to find a value for both variables, so for x and for y, that's true for both equations. Now that sounds a little bit abstract, so let me show you what I mean in the next example. So we have two equations right here. So these two equations, these are a system, right? That's a system of equations. It's just those two equations right there. Step one is that we need to graph the two lines and then see where they intersect. So I'm going to start by graphing this first line. So remember graphing, right? I look at my y-intercept first. So my y-intercept is 6, so I'm going to graph a point there at 6 on the y-axis. And then because my slope is 2, that means I have a rise of 2. And then remember, I could put a fraction line underneath it and say that's kind of like 2 over 1. So I'm actually going to go from here up 2 over 1, graph a point, up 2 over 1, graph a point. And then since I have 3 points, right, even after 2, I could draw a line, but just to be more accurate, I'll use 3. Same thing on the next line that I have, y equals 5x plus 3. I'm going to start by graphing a dot at 3 for the y-intercept. And then I'm going to draw kind of a line underneath 5 and make 5 over 1 for my fraction. So that means I have a rise of 5 and a run of 1 for my slope. So I'm going to rise 5, run 1. So I'm going to put a new point there. And then if I keep going, I'm going to run off of my graph. So I can actually go kind of keep following this pattern, right? Instead of going up 5 and right 1, I can go down 5 and left 1 to follow my pattern. And that's just going to give me a little bit more accuracy when I draw my line to represent that equation. So now I want to look and see where do those two lines intersect? At what point do they intersect? So here we can see there's this really nice point right here where the blue dot and the orange dot overlapped, and that's at 1 for x and 8 for y. So that's 1, 8. So that's all great and wonderful if we have access to a graph and to graph paper and we can graph them and look at that dot right there. But what if we don't have graph paper or we're not able to graph? Or maybe what if we actually have like some fractions in our answers and then we can't really eyeball it, right? On this one, it's pretty evident that we're landing right on that point. But what if we had like 1/2, 8? How would we know exactly what that value is? So I'm going to also show you how to solve algebraically, which will always, always, always give us an exact answer, even when we have fractions or decimals, or even when we can't graph our answers, we can find our answer this way as well. So I'm going to start by looking at my equations, and I notice that both of my equations are equal to y, right? 2x plus 6 is equal to y, and 5x plus 3 is equal to y. Since they are both equal to y, that means that the right side of the equations must be equal to each other, right? So this is a method called substitution. And that means that I'm going to take out the y, right? I know that both of these equations are equal to y, and I'm going to replace the y in the first equation with all this stuff from the equation down here, okay? So my new kind of version of this equation that I've created looks like 2x plus 6 equals 5x plus 3, and I kind of have them flip-flopped from what the arrow I drew here. So basically we're saying 2x plus 6 equals y, and 5x plus 3 equals y, which means they're both equal to each other. So if you ignore everything else that's going on over here, look at this equation. This is an equation that we know how to solve. We even solved a bunch of them in lesson 2 earlier this week. We've done the balancing equations thing. So I'm noticing that I have 2 x's on the left and 5 x's on the right. If I think about doing my balancing balancing equations idea, I'm going to remove two x's from both sides of the equation. That gives me 6 on this side and then 3x plus 3 on this side. I'm totally going to run out of space here. But I'm going to take away 3 blocks, right? Remember thinking about our blocks in our bags situation. So I'm going to remove 3 there, and then I'm actually going to move my work up here. So that means on the left side, I have 3 with my equal sign here, and then a 3 here. And then I need to divide both sides by 3 to get x by itself, or I could even think 3 times what equals 3 on the left. This looks like x is going to equal 1. So what do you notice about that x value that we just solved for algebraically? It ends up being the exact same as that point that we've graphed right here. So how do we find the y value of each equation, right? Remember we said that our goal is that we want to find a value for each variable that works within both of these equations or makes both of these equations true. Well, I can actually take the x that I found and plug the x back into the equation and see what happens. So I'm just going to sort of mental math do this. On my first equation, if I have y equals 2x plus 6, if x is 1, 2 times 1 will be 2, and 2 plus 6 is going to equal 8. Aha. And then if I do on my second one, 5 times 1, that's going to be 5. And then 5 plus 3 is also equal to 8. So now that I've done that, I can see that when I plug my equation in up here, when I use substitution and make an equation and solve it, I actually get the exact same thing that I would get when I graph. So if graphing is not an option, it's always an option to just make the equations equal to each other and solve them and then plug back in for x, and you'll be able to get the same point. And this point is called the solution. This is our answer. It tells us where the two lines intersect with each other. So let's say I give you a system of equations like I've given you here, y equals 2x and y equals negative x plus 3, and I don't give you a graph. So I don't have a graph. I'm not able to just kind of sketch these out and draw them, don't have access to paper for whatever reason. So I'm going to set up an equation using substitution. So again, I see that both of these equations are equal to y, which means that both of the right sides that involve the x are also going to be equal to each other. So I'm going to say 2x, that first equation, is equal to negative x plus 3. So now I need to take a minute and go through, since this is an equation that only has x in it, I can go through and solve for x. And this is going to be a little bit different than thinking about it with the boxes and the bags because we had that negative x going on there. So I don't really want to deal with a negative x. I'm going to add x to get rid of it on this side. And if I do it on one side, I'm going to add it to the other side as well. So over here I have 3x, and then on this side I have 3. This is looking pretty similar to our last one. So I'm going to say, okay, 3 times what equals 3? It looks like x is going to have to equal 1, okay? So hooray, I found 1. But remember that when we are solving systems of equations, we're dealing with multiple variables now, right? I found x, but I still haven't found y yet. So I'm going to need to go back into my equations in my third step that I've written down here and plug x back into the original equations to figure out what y should be. And my goal is that y should be the same for both equations, right? So if I plug it in to this first equation, 2 times 1, that's going to give me a y value of 2, right? If x is 1, then y is equal to 2. If I plug in 1 to the second equation here, I'm going to make it negative 1 instead of negative x plus 3. Negative 1 plus 3 gives me 2. So when x is 1 in the second equation, y is also 2. So since those guys match, that's awesome, right? That was our goal. And now that we know that x equals 1, we've also figured out that y is equal to 2. So the interesting thing about how we have to write our answers is we always write our answers as an ordered pair. And that means that we just write them as an xy point, right? So remember we put our x first and our y second. So this is our final answer right here. This is going to tell another mathematician who comes in and looks at your work that we know that the point where these two lines intersect, if I was going to graph them on a graph, is going to be at 1, 2. So just in closing here, I'm going to double check my graph, right? So I just did all the work algebraically using substitution and solving these two equations. But if I graph that first equation, I'm going to graph it in blue here. Notice that it doesn't have a plus b. That means my b or y-intercept value is 0. I'm going to go 0, up 2 over 1, up 2 over 1. There's my first line. My second line starts at 3, right? My b value is 3, so I'm going to put a dot on the y-axis at 3. And because my slope here is negative, that's really like -1. And then if it's -1, it's really like -1 over 1, which means that I'm going to go from the point that I started at. I'm going to go down 1 and then in the positive direction 1. Down 1, -1. I'm going to graph a couple more points there and then draw my line. So again, I'm going to look at where is that point where those two lines intersect or overlap. And this point happens to be at 1, 2, which is exactly what we solved for and found in the last question. So some final thoughts. What if I have two lines that are parallel and they never touch? So here are my equations, and I've already just graphed them for you guys up here. What happens when they never touch? Is there ever a solution? We would say in this case that there is no solution because there's never a point where these two lines meet. What if the lines are always touching? So for example, what if I had the same line, but it's graphed twice on a graph, right? So I'm talking about two different situations, but they're the exact same line. That means that there are infinite solutions because they're touching at every single point along the graph, right? No matter where I am on that line, my lines are touching. So we've actually seen these terms before, right? Infinite solutions and no solutions. So just for a quick summary here, if we want to solve a system of equations, we are essentially looking for the point where two lines intersect. And we're always going to need to write that as an x, y point, which is called an ordered pair, right? So we're looking for x and for y. If we have a graph, we can graph it and just look and find the point, right? See where they overlap. If we only have the equations and for whatever reason we're not able to graph or we're trying not to graph to save some time, we can solve the equation or the system of equations by making an equation, kind of combining the two together and balancing the equation and solving for x. And then remember at the end, you always need to go back and find y as well.